Okay, so today we're going to be talking about something called limiting and excess reagents. It's very similar to stuff we've already set up. As a matter of fact, it's just kind of taking it one extra step. Let's get going. So it says it's something very new, which I mean, to an extent it is. But limiting the excess reagents are pretty much just relooking at what roles the reactants play inside of a chemical reaction. So I want you to think of this before we get started. When you react two different chemicals, surely they both aren't going to be completely used up. So unless you made sure their molar amounts were perfectly balanced. In other words, when you react to things, chances are you're going to have something left over. There'll be an excess amount of something. There's that word, excess amount of something left over when you're all done. And there'll be something else that'll be used up completely. Not both of them will be used up completely, only one or the other. Today, we're going to learn how to predict which one will be used up completely and which one will have leftovers. That's the whole concept of limiting and excess reagents today. Let's get going. So topic 5, this is in your note package. I guess it's on page, what is it, page 27. The law of conservation of mass states that mass cannot be created or destroyed. It is merely rearranged in space and changed into different types of particles. Quantitative analysis, such as titration or precipitation analysis, can be used to verify the law of conservation of mass. Don't worry about that too much. But sometimes one of the two reactants is not completely used up in a chemical reaction. That is because all of one compound has been used up and there is not enough for the other compound to completely react. The compound that becomes completely used up first is known as the limiting reagent. Now, the reason it's called limiting is, of course, it is just limiting how much of a chemical reaction that can occur, right? So in other words, if you had more of that limiting reagent, you wouldn't be so limited in how much chemical reaction would occur, right? So the one that gets completely used up is the limiting reagent. The one you have too much of or you have leftovers of is called the excess reagent. Anyway, here's an analogy. This is, of course, not in your note package. I want you to think about that classic chemical reaction between Diet Coke and Mentos. Now, if you just took a couple Mentos, one or two of them, and you put them inside the Diet Coke bottle, you're going to have quite the violent chemical reaction that occurs. However, I want you to think, after that reaction is all done and all the fizz settles and all that, you still have a lot of Diet Coke left over, right? So in other words, after you did that chemical reaction, you could put a couple more Mentos in there and another chemical reaction just like that first one would happen. Maybe it wouldn't be quite so strong. Who knows? Maybe it would be, wouldn't be. You guys can test it on your own if you want, really. But again, that chemical reaction would continue happening. That's because there's an excess amount of Diet Coke. One or two Mentos is not going to be enough to completely change all the Diet Coke to whatever chemical concoction forms from this. I just don't even know what the chemical reaction is that occurs. But still, you have an excess amount of Diet Coke. So in a reaction like this, your limiting reagent would, of course, be your Mentos. And your excess reagent would, of course, be the Diet Coke. That's basically what the concept we're dealing with is today. But the question that comes from that is, how do you predict which one is the limiting reagent and which one's the excess reagent? How do you know which one you have more of? Do you go by the volume? Do you go by the mass? Well, let's see. All right, so in your notes, steps to solving limiting reagent problems. There's something I'm going to ask that you change here, but we'll start with the first two because I think the first two steps are just fine. Step 1, as always, write a balanced equation for the reaction. It needs to be balanced because those coefficients that go in front of each chemical are, of course, your molar amounts. Step 2, determine the two reagents involved in the reaction. It's just going to be the things that are the reactants, right? So in other words, the stuff on the left side of the chemical equation, those are going to be your two reagents. Now, step 3, I completely and fundamentally disagree with. So whatever, I think there was some teacher somewhere else that put this together. You know, all due respect to her, but I don't agree with this. So I'm going to ask that you cross out question 3. I'm not even going to bother reading it to you because it's just that not good. And we're going to rewrite this just underneath it. Don't worry, it's only going to be one real quick sentence. Instead of doing this, I want you to actually find 1 mole amount for each reactant. So I want you to write that in there instead of, and so cross out number 3 completely and just write underneath it. You can say number 3, find 1 mole amount for each reactant. So what that means is, with your balanced chemical equation and whatever information you were given, whether it was volume and concentration, or even if it was just your mass, I want you to find 1 mole amount for each reactant. So keep in mind, if you had some sort of chemical reaction, I'm just going to throw in some random things here. Let's say it was like HCl plus 2NaOH. I don't know. I'm just coming up with something here. It's not going to actually balance, but let's just pretend. Let's just pretend that that's what you had on this. Let's say if I gave you the mass of each of these, use the mass and the molar mass to find your number of moles. Notice this one would be 1 mole amount, and this would be 2 mole amounts. That doesn't actually vibe with this, right? You have to find 1 mole amount of each. So whatever mole amount you found for this, you'd have to divide by 2 to get the 1 part, or the 1 mole amount. Okay, that's really important. What they were saying in step 3 here before was they actually wanted you to solve 2 different problems and find the amount of product that you were looking for each of these problems. Step 3 here, as they have written, is like literally 5 times as much work as what I'm going to tell you to do. So just say find 1 mole amount for each reactant. Anyway, step 4, there's only one word we have to change here to make it work with what step 3 said. The species that gives the smaller amount of your, instead of the product, you're just saying the reactant. And if you want to be really specific, the 1 mole amount of reactant is your limiting reagent, right? So in other words, when you find your number of moles of each of your reactants, and then you whittle it down to 1 mole part of each, the one that has the smaller 1 mole amount part is your limiting reagent, because in terms of like an explicit parts of mole, you actually have less of that than whatever else you had. Okay, way easier to go about it this way. It makes your life a lot easier. Step 5, use your limiting reagent to figure out how much of your excess reagent will actually react. So in other words, use your smaller mole amount as your number for doing the chemical reaction. And then step 6, this one's optional. It only happens in certain situations. Subtract the amount found in step 5 from your given amount of the excess reagent to see how much will be left over. So in other words, if you were asked, after this Diet Coke and Mentos reaction happens, how much Diet Coke would be left over, you'd have to subtract the molar amounts to find the molar amount that is left over, and then go from there. That is way easier to see with an example. It's like useless explaining it like that. So we're going to do, ooh, I skipped one. There we go. We're going to do this example here on the next page. If 20 milliliters of 3 moles per liter H2SO4, that's sulfuric acid, is added to 15 milliliters of 5.0 moles per liter KOH, it's potassium hydroxide, a very common base, what mass of water can form? Step 1, guys, write your chemical equation, right? So H2SO4 is combining with KOH. And since that's an acid reacting with a base, 2 things are produced. One thing, of course, is water, which we'll always write as HOH because it shows the H and the OH, plus some sort of quote unquote salt, which in this case, it's going to be potassium and sulfate. So, and to balance out, of course, you need to have 2 potassiums because it had a 1 positive charge, and just 1 SO4 because that has a 2 negative charge. Then, of course, we have to balance this. I know I got to put a 2 in front of this and a 2 in front of this. So that hydrogens are now balanced, OH is now balanced, K is now balanced, and SO4 was always balanced. So we're all good. All right. So here's what you got to do next. So we have our balanced chemical equation. If you look back at your step 2, it says determine the 2 reagents involved in the reaction. It's literally just going to be H2SO4 and the KOH. Those are the 2 reagents. One of them is going to be excess. In other words, one we have too much of, and one's going to be limiting. In other words, it's going to be our lesser amount. First things first, find your molar amounts of each one. We'll start with H2SO4. Notice we know the concentration as well as the volume. Ultimately, we're trying to get moles here. So if we just set this up as 3.0 moles per liter, then that means it's going to equal some number of moles. We'll say it's N over some number of liters. We can turn this to liters by writing it as 0.020. Multiply that over, you're going to see that N is going to equal 0.06 moles. And I want us just to take note right here that since there's technically a 1 in front of this, this represents 1 part, or 1 amount, or 1 molar amount, or however you want to put it. That'll be useful, okay? Next one, let's find how much KOH we have. We know we have 15 milliliters of 5.0 moles per liter, so we'll say 5.0 moles per liter equals some number of moles, I'll call it N again, over some number of liters, which is going to be 0.015. Multiply that over, and you're going to find N is equal to 0.075. Now, you might look at this right now and say, oh, look at this. You have a little bit more of KOH than you do of H2SO4. But calm down, because this represents 2 parts, or 2 amounts, or however you want to put it. We want to compare 1 amount to 1 amount. okay? So since this represents 2 parts, let's divide this by 2. So divide it by 2, and you're going to see that n is actually going to equal, well, I shouldn't say n, my mistake. I should say 1 part is actually equal to 0.0375 moles, okay? Now we notice from this number right here, compared with this number right here, one amount of this, the KOH, is actually less than one amount of H2SO4. So since this has the lower 1 part amount, we have to use this as our limiting reagent. In other words, the amount of KOH we have is limiting the reaction with the excess amount of H2SO4 that we have, okay? So when you do a chemical reaction from here, you use your limiting reagent, right? Because we're looking for what mass of water can form. That means we're looking for how much water will form from this. The only thing that's actually going to do a chemical reaction here with is this amount of moles as 1 part. You can't use the 0.06 moles as 1 part because you would have to have 0.12, so twice this amount of KOH to be able to completely react all that stuff. So it's not going to work. So we have to use our limiting reagent for your mole parts. So since we know 1 part is 0.0375 moles, and we have 2 parts of water that are forming, we know the amount of water that's forming is going to be 0.075 moles. But the question is asking for what mass of water can form. So since we know how much moles of water will form from this reaction, we need to use the molar mass. So the molar mass of water is just 2 hydrogens plus 1 oxygen. I'll let you guys figure that one out on your own, but it's going to be 18.02 grams per mole. So that's going to equal some number of grams over some number of moles, which we know. Multiply it over to the other side. Long story short, you are going to find that you have, to, I guess, just 2 sig digs here, 1.4 grams of water formed. So bottom line here is, get your balanced chemical equation, find 1 molar part for each of your reagents, and the one that has a lesser amount of 1 part is going to be your limiting reagent. Your limiting reagent amount is what actually gets used in the chemical reaction. The other stuff is just excess. You have excess amount of that. You don't use all of that to do the chemical reaction. There will be some left over. This question wasn't asking us to determine the leftover, but some other questions might. So just make sure you are reading that carefully. Question 2, 350 grams of KOH is added to 1 liter of 6 moles per liter of H3PO4, which I think is phosphoric acid. I'm pretty sure that's what it is. I may be wrong. But anyway, what quantity of which reagent is in excess? Okay, so since it's asking for a quantity of reagent is in excess, that's kind of like asking for us or asking us for a leftover amount. Now, when I use the word quantity, I mean either the number of grams or the number of liters. I do not mean the number of moles. The number of moles would be a molar quantity. When we just ask for a quantity, we do want a mass or a volume. But anyway, we'll worry about that as we go closer to this. So I would start by writing out a chemical reaction. I, for whatever reason, always like writing my acid first. So H3PO4 plus KOH is going to form HOH plus the salt, which is going to be K and PO4, but PO4 has a -3 charge and K has a +1 charge, so it's got to be K3PO4. And then we just have to make sure it's balanced, and you just need to put a 3 here and a 3 here. Okay, kind of speeding through that because I'm hoping by now you guys know how to make a balanced chemical equation. Anyway, let's figure out 1 molar amount of each. Let's start with H3PO4. We know the concentration is 6 moles per liter. 6.0 moles per liter. This equals some number of moles over some number of liters, which is exactly 1. It's the most boring reaction or equation there ever, because we now know our number of moles is just 6. Okay, so one part, if we were using this, is 6 moles. Let's figure out this one now. 3 KOH. We know we have 350 grams of KOH, so we need to figure out our molar mass. So the molar mass of KOH is going to be the molar mass of potassium, which is 39.10, plus the molar mass of oxygen, which is 16, plus the molar mass of hydrogen, which is 1.01. I will spare you the time of writing that down. It's going to be 56.11 grams per mole. Now, since we know it's 56.11 grams per mole, we can set that equal to some number of grams, which we know is 350, over some number of moles, which I'll call N. times by n on both sides, divide by 56, and you're going to see that n is going to equal 6.237747 moles. So just like the last question, you might see this number and go, oh, wow, this number is bigger than the other one. We're all good. But remember, just like the last one, this is 3 amounts. So we have to divide this by 3 to find the one part. One part in this case is going to equal 2.079249. And that is clearly, for one part, a lot lower than the H3PO4. So that tells us that our KOH, potassium hydroxide, is going to be our limiting reagent once again. Okay, has nothing to do with the fact that it's a base. It just has to do with, coincidentally, in both these examples, we had a lesser amount of the KOH. Okay, so that is our limiting reagent. That is like our Mentos to our Diet Coke here. Anyway, so from here, we actually don't have to do the same kind of reaction we did before, because we're not actually predicting how much of these are produced. The question was asking what quantity of which reagent is in excess. Well, we know it's going to be our H3PO4, but we're asked what quantity will be in excess. In other words, how much is going to be left over after this reaction? Well, let's put it this way. In this chemical reaction, we're only using 2.079249 moles of one part for each of these, right? So in other words, since H3PO4 is only one amount, we're going to use that one amount being this, okay? We actually have, though, 6 moles of H3PO4. So our leftover amount is going to be 6 moles minus 2.079249. And our leftover amount is going to be 3.920751 moles. That is going to be how many moles of H3PO4 is left over here. But again, like I mentioned at the beginning, we're looking for a quantity that is not, measured in moles, that is actually measured in either grams or liters. And since all we know about our H3PO4 is moles per liter, we're going to have to use that to figure out how many liters of H3PO4 will be left over. So long story short here, let's use that 6 moles per liter. 6.0 moles per liter is going to equal some number of moles, which we'll say is the 3.920751 leftover moles, over some number of liters, which I'll just call X. Times by X on both sides, divide by 6, and you're going to find that to just 2 sig digs, our X is going to equal 0.65 liters. So in other words, after this chemical reaction is all said and done, we'll have 0.65 liters, or in other words, 650 milliliters of H3PO4 left over that wasn't actually used. Okay? Hopefully that makes some sense. We'll do a few more examples here real quick. I don't want to use up too much of your time. 10 liters of nitrogen gas at blah, blah, blah. You can read the whole thing. It's going to be an ideal gas law question, clearly, because we got all these pressures and temperatures. First things first, before I even start this, I'm going to change all my temperatures into Kelvin just so I'm all ready to go for later. Remember, to change to Kelvin, you just add 273.15. So that means 35 Celsius is 308.15 Kelvin, and 40 degrees Celsius is 313.15 Kelvin. This question is asking us for what mass of ammonia gas will form. We're forming ammonia gas from nitrogen and hydrogen, so let's just write out that balance equation. Nitrogen gas is N2, hydrogen gas is H2, and ammonia is NH3. So in order to balance this, we have to make our nitrogens and hydrogens and stuff all match. I think I'm going to times the NH3 by 2, so my nitrogens now match. And now you'll see that I have 6 hydrogens on the right side, so I'll need to turn this into 6 hydrogens by multiplying it by 3, and now that's balanced. From there, we have to find our molar amounts. Now, because of all of these numbers that we were given here, we're going to have to use the ideal gas law, which said PV equals nRT. And remember, R is always 8.31. So for each of these, we'll start with the nitrogen first. We know we have a volume of 10 liters and a pressure of 105 kilopascals and a temperature of 308.15. So if we throw that in, we'll say we have 105 times 10.0 equals N, which is what we're looking for, the number of moles, times 8.31 times a temperature of 308.15. Divide away the 8.31 and the 308.15 on both sides, and you're going to find that N is going to equal 0.410040 moles. And also recognize that because there's technically a 1 in front of this, that represents 1 part. Okay, now let's try this one, H2. We know it has a pressure of 95 kilopascals, so 95 times a volume of 33.5 equals N times 8.31 times a temperature of a little bit higher, 313.15. Divide those two things away, and you're going to see that N for this one is going to equal 1.222968 moles, which is clearly way higher than this. But once again, seems to be the common theme here. This is actually representing 3 parts. We want to compare 1 part to 1 part. So if we divide this by 3, you're going to find that 1 part of your H2 gas is 0.407656 moles. Now that's super close to 1 part of this. It's just a little bit smaller, but it still counts. Since this one is a little bit smaller, that means our H2 is our limiting reagent, right? That is going to be the actual 1 part mole amount that'll be used in this chemical reaction. So if we're looking for what mass of ammonia gas will form, we need to realize that this amount right here, 0.407656 moles, is the 1 part that we're going to be using. For the ammonia, notice 2 parts form. So we need to just times this by 2, and that'll give us 0.815312. That was messy. I'll try that again. 12 moles is what we're going to be producing for our NH3. And we want to turn that into a mass. So if we have moles and we want mass, we need to use the molar mass of NH3. Well, the molar mass of NH3 is going to be the molar mass of nitrogen, which is 14.01, plus 3 times the molar mass of hydrogen, which is 1.01. I will write it out this time around. So 14.01 plus 3 times 1.01. That is going to give us 17.04 grams per mole. Set that equal to some number of grams. That's what we're looking for. So I'll call it X over some number of moles, which is the 0.815312. And if you multiply it over to both sides, you're going to see that X is going to equal to 2 sig digs, 14 grams. There it is. Okay. The whole idea here, guys, I know I'm kind of like repeating myself here, but the whole idea here is just make sure you find your 1 part amount for each of your things that are reacting. And the smaller amount is going to be what we call the limiting reagent, which is actually what is reacting in the chemical reaction, because you have too much of the other stuff. So you have to use your limiting reagent. That's what's actually reacting. The other stuff is just left over. One last question. We're going to be done right after this. You got this much NaOH, and you're adding it to this much HNO3. Calculate the mass of water that forms. Determine your limiting and excess reagents. Finally, use your limiting reagent to figure out how much excess reagent is present. Whew, this is like 2 questions in one. So not only are we calculating the mass of our product, we're also figuring out how much excess reagent is present. In other words, we're looking for our leftovers here. As always, start with a balanced chemical equation. That's going to be NaOH plus, I don't know why I put the base first this time, it doesn't really matter, but HNO3 is the next thing. That's going to react, I'm going to change that because that needs to look like a 3, there you go. That's going to react to produce water, HOH, plus some sort of a salt, which in this case is going to be NaNO3, and that actually is ionically balanced right there because it's a +1 and a -1 charge, so they're already good. And would you look at that, the chemical equation is also now balanced. You don't even have to have any coefficients here. So we can just hop right to it. NaOH, we have 5 grams of it. In order to figure out how many moles, we need to use the molar mass of NaOH. So find the molar mass of Na, which is 22.99, plus the molar mass of oxygen, which is 16, plus the molar mass of hydrogen, which is 1.01. Long story short, if you add that all up together, it's going to give you a very nice 40 grams per mole. Set that equal to the number of grams you have, which is 5, over the number of moles, which is N. So N is going to equal 0.125 moles. Hold on, there we go. That is representing 1 part, okay? So 1 part is 0.125 moles. Now let's do the same thing to this HNO3. Notice this time around, though, we had a concentration that's almost nicer to work with. 1.25 moles per liter equals some number of moles, which is what we're looking for, divided by some number of liters, which is going to be 0.050. Multiply it over, you're going to see that N is going to equal 0.0625 moles. And this, once again, also represents 1 part. Since those both represent 1 part, you just look at them directly. Which one's the smaller number? Bingo, bango, bongo. That one's a smaller number. So guess what? This is our limiting reagent, which is what's actually going to be used in the chemical reaction. Since this is what is actually being used in the chemical reaction, we're looking for the mass of the water that will form. We have to realize that this number of moles is the same thing as the number of moles of water which will form, because it also has one part just like all these others. So we take the 0.0625 moles of water that will form, and we'll have to use it in some sort of a calculation to figure out our mass. Well, how do we connect moles to mass? Of course, it's molar mass. The molar mass of water we had just on a previous slide is 18.02 grams per mole. Set that equal to some number of grams over some number of moles, which we actually know. Multiply it over, and you're going to find that X is equal to 3 sig digs, 1.13 grams. And that is how much H2O will form. H2O formed. Good. All right, so we got the first part of this question done. Believe it or not, there actually is a second part to this question. It says use your limiting reagent, your LR, that would be this guy, to determine how much excess reagent is present. So in other words, figure out how much, that's a quantity, we can assume the leftover amount of your excess reagent is present. Well, your excess reagent is your NaOH. You actually have this much moles of it, but you're only using one part of this one, so you're only using that much. So the amount of leftover will be 0.125 moles. That's how much you had in the first place. Take away how much you're going to be using, so 0.0625. And that actually coincidentally gives you 0.0625 moles leftover. But we want to figure out how much excess reagent is present. So when we say how much, it's not just going to be a molar amount. We like using, more measurable amounts. So let's actually turn this into grams. We have the molar mass of NaOH already. It's 40 grams per mole. We're looking for our number of grams. Divide that by the number of moles that we have left over. Multiply it over, and you're going to find that X is going to equal 2.50 grams. And that is our leftover NaOH, we'll say. Okay, and it's good to label that because, of course, otherwise you'd have two masses in boxes on this page, and you might get confused which one was which, right? So as long as you just label it, it becomes a little bit more clear. Anyway, that was way longer of a lesson than I was expecting today, but for practice, I want you guys working on page 30 to 34. I know there's a metric ton of questions in there, but just kind of piece through them one bit at a time. Give you a bit of a heads up. Question 1C, it mentions water in that question. Water is just a catalyst in that question, right? So in other words, you don't have to worry about it in the balanced equation. Again, that was just for question 1C. As always, if you guys need me, you know how to find me. Best of luck.